Have you ever just looked at the world around you and wondered, what is all this stuff really made of? I mean, what are the fundamental building blocks of, say, your chair, the water you drink, or even the air you're breathing right now? Well, in this explainer, we're going on a journey deep into the heart of matter. We're going to go from the stuff we can see and touch all the way down to the tiny, invisible particles that make it all happen. Let's get into it. So here's our roadmap. First up, we'll see how scientists actually organize all the stuff in the physical world. Then we're going to tackle what purity really means. And trust me, it's not what you think. After that, we'll uncover the unbreakable rules for how things combine, learn how to speak the language of chemistry, and finally, we'll dive right inside the atom itself to meet the particles that make up everything. All right, let's start with the big picture. How in the world do scientists begin to make sense of the just infinite variety of substances out there? Well, it all starts with one simple idea: classification. Okay, think about the last time you were at the grocery store. You've definitely seen labels that say pure butter or pure salt, pure juice, right? And you probably thought, great, nothing extra added. But here's the twist. From a scientific point of view, almost none of those things are actually pure. And this slide right here gets to the heart of it. In our everyday language, pure just means no junk has been added. But to a scientist, pure is way, way stricter. It means every single particle in that substance is chemically identical. So that orange juice, it's actually a mixture of water, sugars, proteins, and all sorts of things. And believe it or not, most of the world around us, from the soil under our feet to the seawater in the ocean, is made up of mixtures. So this brings us to the first major dividing line in all of chemistry. Every bit of matter can be sorted into one of two big buckets. It's either a mixture or it's a pure substance. A mixture is pretty much what it sounds like. It's made of different things that are just physically mixed together, but they're not chemically bonded. A classic example is salt dissolved in water. You can still taste the salt, you can feel the water, and hey, if you boil that water away, you get your salt right back. The salt and the water haven't fundamentally changed at all. Now, on the flip side, you've got a pure substance. This is the complete opposite of a mixture. It's made of only one type of particle. So think about pure sugar or that salt we just mentioned after you've boiled off all the water. Every single particle is identical to every other particle. Its chemical makeup is the same through and through. Now, even pure substances can be broken down into two types. The first is an element. The famous French chemist Antoine Laurent Lavoisier defined an element as something you just can't break down into anything simpler using a chemical reaction. Think of the periodic table: oxygen, iron, gold. These are the absolute rock-bottom building blocks of, well, everything. The second type of pure substance is a compound, and this is where things get really cool. A compound is what you get when two or more of those elements are chemically bonded together to create something totally new. And the keywords here are chemically combined and fixed proportion. This table really breaks it all down. In a mixture like our salt water, everything's just physically jumbled together. You can add a little salt or a lot of salt, it's still just salt water. But in a compound, like water itself, the elements are chemically locked together in a super specific ratio, and the thing you create has brand new properties. I mean, think about it. Hydrogen is an explosive gas, oxygen is a gas we need to breathe, but when they combine chemically, you get liquid water. Totally different. Okay, so we know that elements combine to form compounds. But how? Is it just random chaos, or are there rules to this game? Well, as it turns out, there are two fundamental laws of chemistry that set the stage for everything else. The first rule, thanks again to Lavoisier, is beautifully simple. In any chemical reaction, mass is conserved. Basically, the total weight of everything you start with has to equal the total weight of everything you end with. You can't just make matter appear out of thin air, and you can't make it vanish. It just changes its form. The second rule, from Joseph Proust, is called the law of constant proportions. And this is a game changer. It says that any given compound always, and I mean always, contains the same elements in the same exact proportion by mass. For instance, water is always made of hydrogen and oxygen in a 1:8 mass ratio. Doesn't matter if you get that water from an iceberg, a river, or make it in a lab, that ratio is constant. So you've got these two amazing laws, but for a while, nobody really knew why they worked. What was the underlying reason? Well, the man who finally cracked the code was a British chemist named John Dalton. Dalton's atomic theory was an absolute bombshell. He suggested that all matter is made of these tiny little particles called atoms. He said atoms can't be created or destroyed, which, hey, perfectly explains the conservation of mass, right? And he also said atoms combine in simple whole number ratios to make compounds. And that, right there, is the explanation for the law of constant proportions. It was a simple, elegant theory that just made everything click into place. So now that we have this awesome theory about atoms, we need a way to, write it all down. How do we talk about these compounds? Well, this brings us to the language of chemistry, chemical formulas. To really get a handle on chemical formulas, we first have to talk about ions. An ion is basically an atom that's not neutral anymore. It has an electrical charge. This happens when an atom either gains or loses electrons. If it loses electrons, it becomes positively charged, and we call it a cation. If it gains electrons, it becomes negatively charged, and we call that an anion. Now, an element's combining power has a name. It's called its valency, and it's directly tied to the charge of the ion it usually forms. So if you look at the slide, you can see sodium has a valency of 1, forming a +1 ion. Meanwhile, oxygen has a valency of 2, forming a -2 ion. This valency is the key to figuring out how elements are going to pair up. So how do we actually use this valency to write a formula? There's a really handy little trick called the crisscross method. You just take the number of each ion's charge, forget the plus or minus for a second, and you make it the little number, the subscript, for the other ion. So for magnesium, Mg2+, and chloride, Cl-, you take the 2 from the magnesium and give it to the chlorine. You take the 1 from the chlorine and give it to the magnesium. That gives you MgCl2, a perfectly balanced formula. All right, for our final stop on this tour, we're going to zoom in one last time. We've gone from everyday stuff all the way down to atoms. But what happens if we try to peek inside the atom itself? And here's where the story takes another huge turn. Dalton's theory was a massive breakthrough, but he got one major thing wrong. He said atoms were indivisible, the smallest possible thing. Well, it turns out they're not. Scientists soon discovered that atoms themselves are made of even smaller, more fundamental particles. And here they are, the big three. The atom is made of 3 fundamental particles. Right in the center, in a super dense core called the nucleus, you find the positively charged protons and the neutral neutrons. These two give the atom almost all of its weight. Then, buzzing around outside the nucleus are these incredibly tiny, negatively charged electrons. It's the number of these particles that makes an atom of gold different from an atom of oxygen. So our understanding of matter has been this incredible journey, right? We've gone from simple ideas about purity to the fundamental laws of chemistry, to Dalton's brilliant atomic theory, and finally, to discovering the tiny world inside the atom itself. Each step was built on the one before it, constantly sharpening our picture of the universe. And it really makes you wonder, what fundamental ideas we hold as true in science today might just be the outdated theories of tomorrow?